13.6 and 13.7. Right now we're going to be talking about compound inequalities. First, let's do a quick review. And to do that, we're going to fill out the missing information. On the first row, it says x is greater than -3. And we have that represented as an inequality and in set builder notation. So we're being asked to graph it on a number line and in interval notation. So the number line would look like this. I would draw a number line and label -3 with an open circle, and I would shade the greater than side just so it's a little bit thicker, and an arrow heading off this way, implying that it goes on to infinity. Interval notation, smallest number first, -3 to infinity, doesn't get to 3, doesn't get to infinity. And so I want you to try the rest and see if you can do that as a review of this older information. I'm going to read example 1 to you. When purchasing a life vest, a person is not likely to find one designed for his or her exact weight. Life vests are manufactured to support a range of body weights. A vest approved for children supports a weight of 30 to 50 pounds. This means if a child's weight is W, the life vest is safe if W is larger than 30 or equal to 30, and if W is smaller than or equal to 50. Life situations are often constrained by two limits of reality. You're going to take these two inequalities and graph them on a number line in inequality notation, set builder notation, and interval notation. Compound inequalities, like the one I just talked about a moment ago, contains inequalities joined by an or an and. The one that we just did above, it was joined by an and. It's more common to have or in math. In math, or means either or both. The unit of set A and set B is the set of all elements contained in either A or B or both A and B. We write A union B to indicate the union of the two sets. We have seen this with domains of functions with denominators. One way to think about this is that the union of two sets is whatever you get if you toss every number into both sets to get a bigger set. That's a visual of A union B. Example 2. Write set A in set notation. A equals the set of elements. And what I'm doing here is I'm just looking to see who is in set A. And I'll list every number in there. Again, it's a good idea to go from least to greatest. Write B in set notation. And now we're just looking to see who's in the set B, 8, 9, and so forth. Write A union B in set notation, which is the same thing as A or B. So that's all the stuff in A, and it's all the stuff in B, and it also includes that intersection region. So A union B is the set of, we'll start with the smallest number again, 2, 5, 8, 9, 10, 13, 15, 17, and 19. I might have missed one, but I think I got them all. You'll notice that even though 9 was in set A and set B, I'm only writing it once. The same goes for 15. Example 3. Write the domain of the function f, where f of x equals 2x over 4x plus 1, and write that in interval notation. So we'll start with the idea that the domain can be any real numbers from infinity to infinity. And in this case, the only place where I would have an issue would be when my denominator equaled 0. So what I'm going to do is I'm going to set my denominator equal to 0 and solve. So now I've found that my denominator cannot equal negative 1/4. It can equal anything else. So in interval notation, I would have my denominator would be from negative infinity to negative 1/4, or there's the union from negative 1/4 to infinity. So far, this should feel a little bit like review. Example 4. Consider the compound inequality of 2x is greater than or equal to 3, or 2x is less than negative 4. Write 3 values of x that are solutions. A solution must satisfy either or both of the 2 inequalities. So let's do an example here. Can we think of an x value that works? Let's use an x value of 3. So let x equal 3. And I could show that if I let x equal 3, I would have 2 times 3 is greater than or equal to 3. 6 is greater than or equal to 3. It worked in that one. But it wouldn't have worked in the other one. That's okay, because it said either or both. It's working in one of them. So let's choose another one. Let x equal negative 3. All right. So if x equals negative 3, we would have 2 times negative 3 is less than negative 4. Negative 6 is less than negative 4. That one works. And again, that one wouldn't have worked in the first, but it is working in the second, and that's okay. Either one is fine. You got to choose one more. So let's do x equals 1.5. All right, so if I did 2 times 1.5, is that greater than or equal to 3? I'm getting that 3 is greater than or equal to 3. Yep, that's true. And if I had put it in the other one, 2 times 1.5, is that less than or equal to negative 4? Is 3 less than or equal to negative 4? No, but that's okay, because it worked in just this one. Either or both is fine. So I have allowed it to equal these 3 x values, and they worked in one of the inequalities, so we're fine. Graph the solutions to the compound inequality with a sketch on a number line. Okay, so what I want to do is solve both of these inequalities for the x in order to get a good number line sketch. All right, so in order to solve this one, I'm going to divide both sides by 2. And I'm going to have x is greater than or equal to 1.5. And this other one, I'll have 2x is less than negative 4. Dividing both sides by 2. I'm going to have x is less than negative 1/2. So on my number line, I'm going to have negative 1/2, and I will have positive 1.5. Again, it's kind of weird that I'm doing decimals and fractions at the same time, but hopefully you forgive me. So x is less than 1.5, so it's heading this way, or x is larger than or equal to 1.5. So we're heading off this way. Now the stuff in between wouldn't have worked, but the stuff on either end is working just fine. Check numbers from each region of the number line. Okay, so we're going to check negative 3. We already did that one from up above. We put in negative 3 and we showed that it worked out. So we've got a new one, x equals negative 1. Or excuse me, x equals 1. So let's put that one in. 2 times 1 is greater than or equal to 3. 2 is greater than or equal to 3. No. So 1 does not work, and 1 would have fallen in this region that we are saying doesn't work, so that's a good thing. And if we check 2, we're hoping that 2 works because 2 is over here. So let's check 2. 2 times 2 is greater than or equal to 3. 4 is greater than or equal to 3. Yes, 2 is working. Write the solution in interval notation. So we'll have from the smallest value, from negative infinity to negative a half, union with next value, and there I just made a mistake. Maybe you see it. I needed to do an inclusive bracket instead of a parenthesis there because it was allowed to equal 1.5. We'll do example 5 together in class. And that seems like a good place to stop this video.